Hello friends, my name is Tushar and today we're going to talk about how to find all simple cycles in a directed graph using Johnson's algorithm. So what is a cycle? A cycle is a path in a graph such that the first and the last vertex is same. What is a simple cycle? A simple cycle is a cycle in which no vertex is repeated twice except the first and last vertex. So in this graph here, we have a bunch of simple cycles. Example 8, 9, 8 or 1, 2, 3, 1. So the idea is to find all such simple cycles using Johnson's algorithm. So there are 5 or 6 other algorithms to find simple cycle, but I found out that Johnson's algorithm is the fastest of them. Also for Johnson's algorithm, I expect my viewers to know how strongly connected components work. In another video, I already talked about how to find strongly connected component using Kosa-Raju's algorithm, and I am also going to create another video about how to find strongly connected component using Tarjan's algorithm. But just for revising it quickly, so a strongly connected component is a subset of vertex in a graph such that all the vertices are reachable from each other. So in this graph here, we have 3 strongly connected components. One is 8, 9 because 8 and 9 are both reachable from each other. Another one is 7 and the third one is consisting of the remaining vertices because all these vertices are reachable from each other. Also for the purposes of Johnson's algorithm, I have numbered these vertices going from 1 up all the way to 9. It is not strictly required, but this is how the algorithm is described in the paper, so this is how I'm going to explain it in this video. So next, let's see how Johnson's algorithm works. First thing we do is we divide this original graph into subgraphs where each subgraph consists of vertices and edges which are part of strongly connected component. Since we had 3 strongly connected components there, we have 3 subgraphs here. So why we do that? Because a cycle is always going to be restricted within a strongly connected component. There is never going to be a cycle which spans over multiple strongly connected components. So for example, this edge here is never going to be part of any cycle. Why? Because if it was, it means that either from 8 or 9 there is a way back to 1, and which would have meant that 8 and 9 would be the part of same strongly connected component as the rest of this vertex. And since they are 2 different strongly connected components, which tells us that there is no way back to 1, which means that edges like this and this would never be part of any cycle. So once we have done dividing into 3 subgraphs, then we look for the least number least number vertex. So the least number vertex here is 1. So first we are just going to work on this subgraph, this strongly connected component subgraph. Also, I have stack, block set and block map data structure, and as we run through the algorithm, I'll show you how these data structures are used. Our start vertex will be 1, which was the least numbered vertex in this strongly connected component. So basically we're looking for all the cycles which start and end at 1. So then we do our DFS starting at 1. So we add 1 to the stack and 1 to the block set. And now we're going to explore neighbors of 1. So one neighbor of 1 is 2. 2 is not same as start vertex, which means that we have not found a cycle. 2 is not part of the blocked set, which means that we can explore 2. So we put 2 into the stack and 2 into the blocked set. Then we're going to explore neighbors of 2. So one neighbor of 2 is 3. So again 3 is not same as start vertex, which means that we have not yet found a cycle. And 3 is also not part of blocked set, so we can explore 3. So we put 3 into the stack and 3 into the blocked set. Then we explore neighbors of 3. One neighbor of 3 is 1, and that neighbor is same as start vertex, which means that we found one cycle. And the contents of the cycle is the contents of the stack. So let's record this cycle. So the cycle will be 1, 2, 3, 1. Then we come back to 3. And then we explore other neighbors of 3 and see if we can find more cycle. So one neighbor of 3 is 2. But 2 is already part of this blocked set. And since we are just looking for a simple cycle, anything other than 1 cannot be repeated. So we cannot continue in this path of 2. So we come back to 3 and then explore another neighbor of 3. So one more neighbor of 3 is 4. So 4 is not same as start vertex, 4 is not part of block set, so we are going to add 4 in both stack and block set and explore neighbors of 4. One neighbor of 4 is 5. So 5 is not same as start vertex and 5 is not in blocked set, so we will add 5 into stack and blocked set and then explore neighbors of 5. One neighbor of 5 is 2. Now 2 is not same as start vertex, but 2 is in this blocked set, which means that we again hit a roadblock and we cannot proceed in that direction because vertex 2 cannot be repeated again in the same cycle. So we're going to come back to 5 and explore other neighbors of 5, but 5 had just one neighbor 2. So what that means is, although we're going to recurse back from 5, I'm not going to remove 5 from the blocked set. Why? Because the way stack is set up currently, there is no way in the current DFS traversal that you could find a cycle which starts which has 2 in it and also which goes through 5, because 5 is going to hit 2. But I'm going to record that if we ever unblock 2, then I'm going to unblock 5. So basically I look for the neighbors of 5 and add 5 to their blocked map. So if 2 ever gets unblocked, at that point of time I will unblock 5. So as you see, I left 5 in the blocked set. Then from 5 we come back to 4. 4 has no other neighbors and we did not find a cycle in this current path. So similar, just like before, we leave 4 in the blocked set, remove it from the stack and also find the neighbors of 4, which is 5, and add 4 to their blocked map. So just saying, like, if 5 ever got unblocked, then we are going to also unblock 4. And then 4 we come back to 3. Now 3 has one more neighbor, 6. So we are going to traverse there. 6 is not same as start vertex and 6 is not same as blocked set. So we add 6 to both of them. Now 6 has one neighbor, 4. Now 4 is not same as start vertex, but 4 is part of this blocked set, which means that we should not explore 4. And this is how we do optimization. Since we did not remove 4 from this blocked set, which means that we saved this extra traversal where we go from 4 to 5 and 5 to 2 and then realize that 2 is already in the current stack and then come back. So by not removing 4 and 5 from the block set, we provided this optimization. So anyways, but we are going to note that if 4 ever gets unblocked, then we should also unblock 6. So 6 has no more neighbors, so we go back to 3. So we remove 6 from the stack, but not from the blocked set. Now we go to 3. So 3 is done exploring all its neighbors and it did find a cycle in one of its neighbors. So 3, we are going to unblock 3 because there is a possibility that there could be a future cycle going from 3 to 1. Since 3 found a path to 1, it means that there could be some other path which could lead from 3 to 1. So we have to unblock 3. So I remove 3 from the stack and I'm also going to unblock 3. And then I'm going to check this blocked map to see if by unblocking 3 do I have to unblock any other vertices, and none, because there is 3 is not part of any key. So then from 3 we go back to 2 because that's where we came from. Now 2 has no more neighbors. So now since we did find a cycle from 2 all the way to 1, which means that we have to unblock 2 to open up the possibility for future cycle. So we'll go to unblock 2, and since now that we've unblocked 2, we have to go and check, is anyone else waiting to be unblocked because of 2? So 5 was, so we go to 5 and see if anyone else was waiting to be unblocked because of 5, and 4 was, so recursively go to 4, and was anyone else waiting to be unblocked because of 4? 6 was, and no one was waiting for 6. So first we remove 6 from here, unblock 6 and remove this particular entry. Then we go to 4, remove 4 from this unblocked block set and then delete this particular entry. And then we go to 2, and 2 is already removed from the block set, but we also got to remove 5 and then remove this particular entry. So as you can see, by the time we were done with 2, and then also we removed 2 from the stack. So by the time we were done with 2, now we have to unblock 4, 5, 6, all these other vertices. Why? Because now that 2 is no more in the stack, there is a possibility of a cycle going through 6, 5 and 4 and leading to 1. So now we come back to 1, and 1 has another vertex 5. So we are going to add, and 5 is not part of this block set. And why? Because since 2 got unblocked, we removed 5, which means that we opened up the possibility for another cycle going through 5. And now that 5 is not part of block set, we can explore 5. So we add 5 to the stack, 5 to the block set, and then we're going to explore neighbors of 5. So neighbor of 5 is 2, and now we'll repeat the process like before. So neighbor of 5 is 2, and 2 is not part of stack, and 2 is not same as start vertex, so we add 2 here, 2 here. And then neighbor of 2 is 3, so 3 and 3, and one neighbor of 3 is 1. It means that we found a cycle, and the contents of the cycle will be this: 1, 5, 2, 3, 1. So we found cycle here. So now we explore other neighbors of 3. One neighbor of 3 is 4, and 4 is not explored, and 4 is not same as start vertex, so we add 4 here. Another neighbor of 4, one neighbor of 4 is 5, but 5 is already part of block set, which means that we cannot explore in the direction of 5 because 5 is already part of this stack, and it's a simple cycle we are looking for. So we go back to 4, leave 4 in the block set, but mark that if 5 ever gets unblocked, then we are going to unblock 4. Then from 4 we remove 4 from the stack, but not from the block set. From 4 we go to 3, 3 has another neighbor 6, we add it to the stack and to the block set. 6 has another neighbor 4, but 4 is already in the block set, so we did not find a cycle from 6 all the way to 1, but we are going to mark that if 4 ever gets unblocked, then we'll unblock 6. So leave 6 in the block set and remove 6 from the stack and go back to 3. Now 3 has explored, 3 has another neighbor 2, but 2 is already part of block set, so we come back to 3. So now 3 has explored all its neighbors, and it did find a cycle leading to 1, so we have to unblock 3. If you ever find a cycle, ever find a path leading to the start vertex, you have to unblock that vertex to open up the possibility for future cycles. So we remove 3 and we unblock 3. And then we check, does anyone else need unblocking? Because of 3, no one else does. So we go to 2. Now since we found a cycle in this path from 2, so we are going to unblock 2, remove 2 from the stack and see, does anyone else needs unblocking? And no one does. So from 2 we go back to 5 and we unblock 5 and remove 5 from the stack and also see if anyone else needs unblocking. Because of 5, yes we do. Because 4 was dependent on 5 to be unblocked, which means that we will remove 4 from here, and then we're going to see who is dependent on 4, and 6 was, so we'll remove 6 from here, and we'll also remove these entries. So finally we come back to 1, and now 1 has no more neighbors to be explored. So basically, after all this, we found all the cycles which starts and ends with 1, and so there are 2 cycles which start and ends with 1. So after we are done dealing with 1, the next thing we do is we remove 1 from my original graph as if 1 never existed before. So we remove 1, we remove all the outgoing and incoming edges from 1 and just delete 1 and act like 1 never existed, and then repeat the entire process again. So let's do that quickly. Now that 1 is not part of the graph, we still have 3 strongly connected components. We again look for the least numbered vertex, which is 2. So our new start vertex will be 2, and we'll repeat the entire process again. So let's do that very quickly. So 2 into the stack, 2 into the block set, neighbors of 2 will be explored. So that will be 3, 3 will be going here, and 3 will be going to the block set. Neighbors of 3 will be explored. One neighbor is 2, so it is same as start vertex. So we found one cycle which will be 2, 3 and 2. Then we go back to 3 and then explore another neighbor of 3 which will be 4. So we add 4 to the stack and 4 to the block set and explore neighbors of 4 which will be 5. So we add 5 stack and block set, and then 5 we end up at 2. So again we found another cycle, and the contents that cycle will be 2, 3, 4, 5, 2. And then we recurse back from 5. Since we found this cycle from 5, there is a possibility of future cycles. So we remove it from the block set and stack, and then we go back to 4. Since we found a cycle in this path, we remove 4 from both block set and block and stack, and then we go back to 3. 3 has another vertex, another neighbor 6, so we explore that. So we add 6 to here and 6 to here, and from 6 we go to 4, and 4 is not in the block set. And now you can see why removing 4 was so critical, because if we had not removed 4 from the block set, we would have never found this cycle going via 6. So we remove 4 is not in block set, so we add it. Then 4, from 4 we go to 5, it's not there, so we add it. And then 5's neighbor is 2, so we found one more cycle. So the content of that cycle will be 2, 3, 6, 4, 5 and 2. And then we recurse back, so we found a cycle, so we unblock 5 for the possibility of future cycle. Then we go to 4, we unblock 4 for the possibility of future cycle. Then we go to 6, we unblock 6 for the possibility of future cycle. Then we go to 3. So at this point of time we have explored all the neighbors of 3. So and since we found cycles, we are going to unblock 3, and we are going to remove it from the stack, and then we end up at 2, and now 2 has no more neighbors. So again we are done finding all the cycles which starts with 2, which is 2, 3, 2, and this one and this one. So now again we go back to this original graph, act like 2 doesn't exist, and then repeat the entire process again. Let's do that very quickly. With 2 gone, these are the remaining strongly connected components here. So there is no reason to pick a subgraph with just one vertex, because there is no possibility of a cycle, because we're assuming there are no self loops in this graph. So then next we pick the least number vertex which has at least 2 vertices in the subgraph, and that will be 8. So with 8 we repeat the same process. So 8 goes into the stack and block set and explore neighbors of 8, which is 9. So 9 goes here, and then explore neighbors of 9, which is one of them is 8. And 8 is also start vertex, so we found another cycle, and the cycle will be 8, 9, 8. And then we remove them from the stack as we recurse back, and then we are done with 8. So once we are done with 8, we'll act like 8 doesn't exist in this graph. So then we'll just be left with strongly connected components, or with the subgraphs whose size is just 1. At this point of time we are done with the algorithm. So in this graph here we found 6 different simple cycles. Let's analyze the time complexity. So the time complexity is O of E plus V into C plus 1, where C is the total number of cycles in the graph. So we can find strongly connected component in E plus V time, which is why we can guarantee that between every cycle the worst time which will pass will be E plus V. But remember, we can have exponential number of cycles, which means that the total time complexity can still be exponential. So, but the only guarantee is that between every cycle the worst time which will pass will be E plus V, and the space complexity also will be E plus V. So next, let's look at the code for this algorithm. Let's first look at all the data structures used in this algorithm. One of them is block set, which is a set of vertices which when blocked will not be explored. Another one is blocked map, which is a map of vertex to the set of vertices. So when this vertex in the key is unblocked, then all the vertices in the values should also be unblocked. And then stack holds the current DFS stack, and then all cycles is the list of vertices. So in this inner list is representing one cycle, and then the outer list is the list of all the cycles. So basically all cycle is going to store my final result. The main function is simple cycles. It takes in a directed graph, and then first we're going to do is initialize all the data structures, and then our start index will be 1, and you remember the indices are the vertices are valued numbered from 1 all the way till however many vertex we have. Then we are going to use Starjan's algorithm to find strongly connected component, So while start index is less than the total number of vertices we have, which initially will be true, first we do is we create a subgraph from the original graph such that it only consists of vertices which are numbered greater than or equal to start index. So anything less than start index will be ignored. So initially start index is 1, so we will include the entire graph. Then in this subgraph we are going to find all the strongly connected components using Tarjan's algorithm. Then we are going to pass this SCCs and the subgraph to least index SCC. So basically finding for the least index vertex among all the strongly connected components. So this method here first creates a graph for each of the strongly connected components, and then among them looks for the least index vertex. Also it ignores any graph which has just one vertex in it because it will never have any cycle. So this might or might not return this might or might not be present. So if the least index vertex is not present, then we break and then we are done with the algorithm and return all cycles. Otherwise, if it is present, then we get the least index vertex, clear the block set and blocked map because they may be populated from the previous iterations, and then find all the cycles in this particular strongly connected component graph which least vertex is part of. So this is the start vertex and then this is the current vertex. And then finally we'll look at this method in a bit, and then finally we increase our start index to be at least index plus 1. So when we go back here and then when we create a subgraph, next time we are going to ignore everything which is less than start index, and this is also we discussed previously in the video. So let's look at find cycles in SCG, which is the main part of the algorithm. So here the first is the start vertex and second is the current vertex. So first we do is we do a DFS here. Found cycle is false. We push the current vertex into the stack, and then we also push the current vertex into blocked set. Then we are going to explore all the neighbors of current vertex. So we get one neighbor at a time. If this neighbor is same as start vertex, it means that we found the cycle. So we are going to push the contents of the stack into this list cycle and add this list cycle into all cycles, because all cycles is storing our final result. And then we are going to mark the found cycle as true because we found a cycle in this particular path going via this current vertex. Otherwise, if neighbor is not same as start vertex and if neighbor is not in the blocked set, then we can explore this neighbor. So we again go into the recursion with find cycle in SCG, keeping the start vertex as same, and for the current vertex passing neighbor, and then it repeats the same process. And then if we did find a cycle in this path, then we set the found cycle to be true. So basically, if for a current vertex, if any of its neighbors finds a cycle in its path, then found cycle will be true for the current vertex. So once we are done with the for loop and all the recursion, if found cycle is true, then we unblock the current vertex. And this unblocking is not just unblocking the current vertex, but it's also checking the blocked map and recursively unblocking all the other vertices which are waiting on the current vertex. So let's look at unblock very quickly. So we remove vertex u from the block set, and then getting all the vertices from the blocked map which are waiting on u, and then going through each of them and removing and recursively unblocking them as well. So as we discussed in the video, this is recursively unblocking all the vertices. So once we are done unblocking, and if the found cycle is not found, so basically if there is no cycle in this path, then we are not going to unblock this vertex, this current vertex, but we are going to find all the neighbors of the current vertex and add this current vertex to their blocked map. So this is because if they ever got unblocked, then we are going to unblock the current vertex as well, and this is also we discussed in the video before. And after this, we are just going to remove the current vertex from the stack, and then if cycle was found, then we return true,
and if cycle was not found, then we return false, and this happens recursively. So finally find cycle comes here, and then we come back to here, and then we increment our start vertex, and then all cycles will have the final result. Let's quickly run this code. So this is the same graph as we discussed previously in the video. So let's look at the result of this graph. So here, this is the list of all the cycles found in this graph. So I can totally understand that this video is code is little involved. So I would recommend is you copy this code and run it and see how the entire code is working. So finally, the time complexity for this algorithm is O of e plus v into c plus 1, where c is the total number of cycles. The reason we have a strong bound here is 2, because 1, we can find strongly connected component in e plus v time, and second, because we are doing all the blocking of the vertex and unblocking it only when required, we are saving on the useless, fruitless and needless searches. And also the space complexity is O of e plus v. So this is all I have to talk about Johnson's algorithm. Please like this video, share this video, comment on this video. Check out my Facebook page, facebook.com tusharoy25, and check out my GitHub link, github.com mission peace interview wiki. Thanks again for watching this video.